All right, yeah.
Okay. Hello everyone. I'm Abhishek, and today we are going to discuss uh, about. So we are reading this book, Designing Data Intensive Applications, and today we have been discussing about the transactions and some of the weak isolation levels in transactions. So last time we have discussed snapshot isolation. Uh, Today we will see some of the problems with snapshot isolation. What are the problems in snapshot isolation, and then how we can use other ways of transactions that are more stronger guarantees. Uh, so yeah. So uh, so by the way, before I begin moving on, are there any questions from the last session? Uh, But are there any questions related to snapshot isolation? Last time we discussed lots of topic. We discussed compare and set. We discussed how we create this conflict-free data structures, which creates a copy of your data, which creates the copy of the data that has been modified, and they don't override the existing objects, right? We discussed that. So that allows your transactions to read the data and not block read. Uh, okay, so we have discussed this conflict resolution and replication, right? So today we have to discuss this right, skew, and factors, right? Okay, so here now we are going to see like what are the problems we can see even with the snapshot isolation, and uh, so then that's why snapshot isolation might not work in all scenarios, and that's why we need those stronger concurrency control uh, uh, concurrency control technique. So one of the thing is right skew, right? So here they have. I think he has not explained it well. So so what exactly is right skew? So right skew happens when uh, so the example given in the book was, let's say there are two doctors, Bob and Alice, and so basically our database constraint is at least one of the doctors should remain on call at a time, right? So now imagine a transaction where uh, let's bring the screenshot. So let's imagine a transaction where so uh, basically at a time we want one doctor should be on call, right? And let's say right now both of these two doctors are true on call. So now let's say both of them decide at the same time that they want to take rest and they want to uh, go off call. So both of them will begin the transaction, right? So both of them will see what is the value of currently on call doctor. So they will be returned both Alice and Bob, right? And they will check that if the value of current on call is greater than 2, means there are already more than one doctors which are on call, then remove me from on call, right? So Alice will see that currently there are more than two doctors which are on call, so we can remove me from on call. Similarly, he will also begin the same transaction. He will see uh, that there are more than two doctors which are on call, so he will remove himself. So here he will remove Bob, here he will remove Alice. So now at the end of both of these transactions, we will see that both the doctors have gone off call, right? Uh, so yeah, so this is the problem of right skew, right? So here so this kind of transaction, it has followed all the constraint of transactions which we have discussed before this. There is no dirty write, there is no lost update, right? So by dirty write, we meant that if two transactions uh, execute at the same time, one overrides one of the transaction, right? And then one of the updates is lost, right? So there is nothing like that, but still we have seen that uh, we have created a problem with the constraints of the database, right? Uh, okay, so it is neither a dirty write nor a lost update because the two transactions are updating two different objects, right? You can think of write skew as a generalization of lost update problem. Write skew can occur if two transactions read the same object and then update some of those objects. Different transactions may update different objects. Automatically preventing write skew requires true serializable isolation. The second best option in this case is probably to explicitly lock the rows that the transaction depends on. Right? Okay, so so few interesting things. So you remember we last time discussed that to prevent lost updates and all, what we can do is we can take the lock on the road that we are going to modify and we can apply compare and set, right? Either we can take lock or we can do compare and set. So basically, again, I want to emphasize here is that, so let's say this person, Alice, he was doing the transaction, right? He read that there are these many doctors which have greater than two. So let's say before updating, if he would have taken the lock on Alice, so he could have taken the lock on Alice, right? Because, and this person could have taken the lock on Bob because both of them are independent values they are updating. So that's why taking the locks, they could have still succeeded and gone with updating the values, right? So that's why the strategies which we discussed in the last section, that taking the locks on the values that you're going to modify will not work in this case. So now to avoid, right? One way is that one thing which we can do is that basically this entire transaction, like either these transaction entirely they happen serially, that we allow only one transaction to happen. So when this transaction is happening, this is like waiting in a queue. So we are doing everything on a single thread, right? One option is this. Another option is that whatever values we are reading, right? So here we were reading these values as well. So we are taking on all the values that we are reading because the values which we are reading might change, right? So this transaction was reading these values, and these values have potential to change after the transaction. So basically we take lock on all the rows which we see have potential to change after the end of the transaction, right? So this is one approach, right? So here he has discussed this, that automatically preventing write skews require true serializable isolation, right? Uh, so this is the first thing I mentioned, that either true serializable isolation, either we say that each one of them will happen one after another, or the second best option is that explicitly lock the rows that the transaction depend on. So this transaction depend on this Alice and Bob rows, so they take lock on both the rows instead of only taking locks on the row that it is going to modify. So there were some more examples mentioned related to ride skew, which is meeting room booking system, where you see where you want to book a room and you check if there are any available slots in the room for the time. Then there was this multiplayer games where where two different players are trying to move two different figures at the same position on the board. Then the third example was given was claiming a username, where you check that the username does not exist. And so both transactions will see that this username does not exist, and they both will now create the username. So, okay, so now just moving on. So what is the reason of this right skew? What is creating this right skew? So there is a phantom, there is something hidden which is creating this right skew, where a write in one transaction changes the result of a search query in another transaction is called a phantom, right? So basically, what we're saying is that the write in one of the transaction has modified the search result of another transaction, right? So the write of this transaction has modified the search result of another transaction, right? So this part which was hidden over in this transaction is what is creating a right skew, right? So yeah, so actually I don't, yeah, okay. Any questions or any additions so far? Am I audible?
Yes.
Hello? Yes, you are audible.
Okay. So, by the way, I want to ask one question. Has anyone else also read this section and serializability section?
Yeah, I have read it actually.
Okay. So, am I making sense? Because yeah, I have not like I have read it once, but not in details. Am I correct up till now, or is there anything else I?
Yep, perfectly correct.
Okay. Okay, so now going to materializing conflict. A serializable isolation level is much more preferred in most cases. Uh, if the problem of phantoms is that there is no object to which we can attach the logs, perhaps we can artificially introduce a log object into the database. This approach is called materializing conflicts because it takes a phantom and turns it into a log conflict on a concrete set of rows that exist in a database. Okay.
I think the meeting room, yeah.
This type of situation happens is if you go a little bit up, Abhishek.
Mm-hmm.
So that meeting rooms go down a little bit. So author gave some examples. So the meeting room, booking the meeting room. So if you switch to the another screen where you are showing that screenshot.
Yeah.
So here in that, first we actually get the number of rows, that select query, which tell us that, okay, these number of record exist for Alice and Bob. And then we acquire the solution, author suggested that we acquire the log on those number of rows. and then put an update. So, but in case of meeting room problem, when we run that select room query to check that whether a particular room is booked or not, so that query will return 0. So when the query return a 0 count, so we cannot put any lock on that. So in that case, it will book, multiple user can book the same slot. So to solve that problem, so user suggested that we can put a dummy object, and that select query will return the record, and we will put a lock on that, and then actually only one user will book the meeting room.
Oh, nice. Okay, okay, understood. Yeah. Okay, great.
Another
Yeah.
example, it wasn't like, I mean, this is a good one, but it was a little different for Phantom. It was talking about actually Phantom, yeah, similar issue, Phantom reads and writes. But, and the example they gave was if you're doing some range query, right? Like give me the list of, let's say, I don't know, give me some, list of doctors who shift IDs between X and Y. And then if you try to insert a new record, one transaction is trying to insert a new record between these values X and Y, right? So ideally, if you don't take care of this phantom issues, then a transaction can insert a new value, new row between X and Y, and another transaction, when it reads again, do that same query again, it will return an extra row because of that newly inserted row, which wasn't there before. And using this, avoiding this, then you take a range lock between X and Y, and nobody can even insert data between X and Y that way. I mean, that was another way of handling it, but yeah.
Okay, and is there a name of this technique?
What I am sharing, this is called phantom reads. You're avoiding phantom reads, but yeah.
They also call it as in range index locks, I guess, right? Like
Exactly.
Okay, so you are taking locks on the entire range of read.
Yeah. And then you're not adding any new rows.
And that's possible if the select query is based on an index column.
Okay.
Index column.
Yeah, because we need an index on that specific column, right? Like so on which the select is executed. So automatically the log would be the log could actually relate to the index column, which is actually in sorted order, right? So that's how we are able to take the range logs.
Do we need index column?
I think it is it because to like otherwise it will be very slow if we don't have index on that.
Exactly, right? Like so, yeah. So otherwise, if we don't take especially for these range logs, right? Like so, if we don't take the range log on a column that has an index built into the table, right? Like so, then what would happen is we would have to. We would have no way of. The values are not sorted, right? There is no way to figure out what matches the select column unless we scan the rows, all the rows of the table.
Yeah.
Right. Like so. So that's why. So even for that meeting room example, they basically give two options where you can actually either take the range log on the room. If an index on the room exists, right? Like so, for the room number, you can take the range log, or you can take the range log on the specific time slot. If the index is on the time slot column. So,
so Johnny, is that like you're saying it's more for optimization, but what if there is no index? It can still be done, right?
Oh yes, so it can still be done, but it has to even figure out to execute that select query, right? Like it has to scan all the rows of the table.
I know.
Yeah, makes sense. And another question. So the approach of materializing conflict, which Praveen has talked about, that you create a dummy object and take a lock on it. So is that something that the application has to do, or will the database do it for us? Like, do the database provide this functionality? Has that been mentioned? So like if I'm doing like this, will the database create a dummy object and handle it, or I have to do it. I have to.
A
So
to B.
materializing conflict means you are actually creating that object that you're trying to lock on.
Okay, so so the application has to do it.
Yeah.
Yeah.
Okay. Okay. Okay.
So even in MySQL, there is a query like select for update that actually locks the row which you are trying to select. But if the row doesn't exist for that condition, the lock won't be acquired.
Yeah,
Same
and
thing.
so,
Yeah.
and so it might still create problems in these scenarios, like where we were searching for unique username and all, right? Where there is no row that exists for that username. So there will be no locks taken, and still we can create two users with the same username.
That might be handled internally by index. I mean, the index might be one of the ways.
How will the index help? Because in that case, so the example where you are creating a unique username, if you are running a select statement, so with the
Yeah,
select
yeah.
statement, there will be. Uh-huh.
Yeah. So, I mean, the first insert will be successful, and second insert, the database won't allow you to do that.
That specific case of
Index is like a
username.
unique.
Yeah, if you have a unique constraint.
Yeah, if you have, that is a workaround if you have unique constraint. But uh, the example is, let's say your initial check was that if there is no username like this, then I will add the value. Then with just that check, you will create a problem, right? Because you will see that in two transactions, that username does not exist, and you will append it. Unless you have these additional constraints like that.
Abhishek, that would be similar to, let's say, if I even write an update query, right? Where I say, for example, here as a thing, like you have update doctors, set this, where condition, right? The condition may not be true. Like there might not be any record with this name and shift ID. In that case, you don't need to update, right? So from what I know, if you run an update query like this, or like that, if basically this is like an if condition, right? You're saying if these conditions are met, then update this record.
Yeah.
So what happens is there are two types of locks that are used. When you are just evaluating the rows, that which one will be updated or not, whether this qualifies for an update, you acquire an update lock, right? And the moment you recognize that yes, I need to change this row, then you switch to an exclusive lock, right? And this exclusive, and then let's say another query comes in, a select query, where it says select from doctors, where name is Bob and shift ID is this, right? Unless that first transaction, which is working on either an exclusive lock or an update lock, right? Unless that transaction is committed or aborted, the read query, which works on shared lock, will be stuck. It won't be able to finish. So because the basic idea is that the shared lock and the exclusive or update locks are not compatible.
So why did we take two different locks? So basically, if we are having, so to check the condition, you said we will take shared lock, right?
No. We'll take update lock. Check condition is update U. Like there is a U lock, there is an X lock, and there is an S lock. S is shared, right? So when you're evaluating, you take an update lock, right? Which is not compatible with the shared lock. I have to check, but that's how it works. And exclusive is definitely not compatible with shared. Uh, so
So, no, like my question is, why do we have to take two different kind of locks? If we take just one lock, what is the problem with one lock?
can you maybe I didn't capture your question completely. Then can you outline the scenario again?
So in this scenario itself, you talked about two different kind of locks, right? One, you will take this update lock, and another you said you will take a shared lock. I'm saying first, what is the difference between two? But like,
Yeah.
I'm just asking that, let's forget about the difference. Why is that one lock not enough? Where you take?
So this is how databases work, right? It's a compatibility. So maybe I can share that matrix. If you even Google right now, I don't have top of my head, but the idea is that there are certain locks which will work with certain other types of locks. And the idea, if I think about your question again, why there are two different types, it's more like saying, why do we have a write transaction and a read transaction? Why don't we just call it transaction, right? Because the nature is different, and the exclusive and update locks are linked with the write, operations, and shared lock is handled by the read operations. So the nature of operations is different, and the locks compatibility is different. Like if you look at, I think there is a table which shows how shared lock is you can, if a transaction has acquired a shared lock, and if another transaction comes with like two readers sort of, right, they'll
Oh, okay.
that way.
Yeah.
But I don't remember the table, like, but that's the intention, like.
Okay, I got it. So it will be something similar to like read lock and write lock, right? So basically, with read locks, why we take different locks is, so with read lock, we are saying that uh, with read locks, other transactions are allowed to read, right? So multiple transactions can increase the read count and take the read lock. But when we are doing write, then during the write, nobody else is either allowed to write as well as read, right?
Right.
Because, so, okay.
And based on the isolation level where we play games.
Yeah. Okay. Yeah. Okay. So, yeah, another thing I want to mention is, so once I was, so someone asked me this question some time back, and uh, it is so basically linked list, right? You have a linked list and you want to do some operations on that linked list, and it is a multi-threaded environment, so multiple threads could be doing those operations. So basically a simple question, right? That in a linked list you want to insert a node, delete a node, and all those things, right? So we have learned how to do it on a single thread. But now what if multiple threads are doing the same thing? So probably we can discuss that sometime, but if you do solve that problem, right, you can apply a lot of these techniques over here and come to a solution. Like one simple solution is what has been mentioned in the book is you serially do things, right? So you take the lock on the entire operation. You don't allow multiple threads to execute at the same time. So then it just behaves like a single threaded environment. But then the problem is then your system becomes slow. You are not taking the advantage of multiple threads. So then the next approach comes is that you take locks only on the object, on the nodes which you think will be modified, and then do those operations. So probably we can discuss that problem sometime, and that will help understand a lot of these things.
So one additional information regarding this problem, right? Like, so this was my on-site interview question at Cloudera 6 years back.
You also had this question, nice. Yeah.
6 years back, in 2014.
Yeah. Mm-hmm. Oh, so so do you want to talk about your experience, or you are just saying that you also had?
I just upvoted your question. So
yeah, and
because it's a pretty popular question.
Yeah, and I think I have also faced this question 2 times. So that's why I always wanted to discussed this question with a group of people.
Right.
So yeah.
And that range lock actually perfectly applies over here, right? Like, so when you want to modify a node, you basically take a log on not just that node alone, but at least one node before and one node after, so that because of the way you change the pointers and stuff.
Exactly. So that was one thing, and another thing which I thought of applying on this approach was that rather than modifying in place, so rather than when you have to do a write, rather than you start modifying the linked list and then doing those insert operations, you create a copy. You create a copy of the new node structures that you want to create, and then add it. So the advantage of creating a copy and then atomically swapping is that you don't need to block reads. But if you modify the linked list in place, then you have to block the reads also, because while you are performing the write operations, your linked list might be in an inconsistent state. So which means that your links might have been broken for some time, because when you're writing, you're updating those links, right? So they might have been broken. So that's why if you're doing read, your read might see incorrect values. So that's why not to modify in place, but creating a copy and then doing your operations. So which was the approach which we have discussed in the last section, right? Where they said that when modifying B trees and all, rather than modifying B trees in place, you create a copy of B tree, you create a copy of that page, and then start referencing to that new page. So on the similar lines. Okay, so now we were talking about serializability. So now our serializability is our strongest isolation level. So basically, the meaning of serializable is like happening one after another, right? So serializable isolation is usually regarded as the strongest isolation level. It guarantees that even though transactions may execute in parallel, the end result is same as if they had executed one at a time serially, right? Without any concurrency. So there are three techniques. One is like literally executing transactions in a serial order, right? So you block those transactions one by one. The second approach is two-phase locking. So this is also very famous, two-phase locking. We will discuss about this. And the third is optimistic concurrency control techniques such as serializable snapshot isolation. Okay. So yeah, so there are these three approaches. Let's discuss one by one. So first approach is actual serial execution, right? So in actual serial execution, we are using a single thread, and so we are saying that we have removed the concurrency entirely. We will execute the transactions one after another, right? So now one may argue that if you're doing like this, your system will become very slow, right? Because like each of the transaction is happening serially on a single thread. So with multiple transactions, it might take a lot of time. So why this approach works these days? Because a lot of databases are in-memory databases. And so in those in-memory databases, if you want to perform some updates, they are very fast. So that's why even if you do the transactions serially, you don't have a huge performance penalty, and you can go on with executing them one after another. So this is what they mentioned. So two reasons: RAM became cheap enough that many of the databases are all in memory, and database designers realize that OLTP transactions are usually short and only make a small number of reads and writes. So they are saying the second thing is, even if your database is not on RAM, OLTP, right? Online transactional processing, where you are just modifying few number of rows or you're making few number of reads and writes, that are also comparatively fast compared to OLAP transaction, online analytic processing, where you're doing a large reads and large writes, right? Those are the transactions which take a lot of time. So that's why those databases which are meant for OLTP transactions, they can execute the transaction one after another. Sometimes perform better than a system of that support concurrency because it can avoid the coordination overhead of locking, but its throughput is limited to that of a single CPU core. Yes, okay. So the point here is that so when you are doing concurrent operations and when you are doing locking and all those things, right? So there is some overhead which is added with this locking mechanism where your system has to acquire that lock, then perform the transaction, and then release those locks. So this locking mechanism is also overhead. So that's why if you avoid this locking strategy and if you do these transactions on a single thread where you don't need locks at all, then this system can perform better. Like in those scenarios, this system can perform better. But again, the point is that now your system is behaving like a single CPU core system, so its throughput is limited to what a single CPU core would be doing, right? Because you're not taking advantage of multiple threads. Okay. So yes, so then moving on to encapsulating transactions in stored procedures, right? So another approach which has been mentioned, which I understood, and correct me if I'm wrong here, so which is that so multiple, so basically that set of operations, so those multiple set of operations that you have to do, you create a procedure of it and then you store that procedure in the database. And now the database, whenever it will execute that procedure, database will execute it serially, right? So system with single threaded serial transaction processing don't allow interactive multi-statement transactions. So instead, the application must submit the entire transaction code to the database ahead of time as a stored procedure. Has anyone used this stored procedure approach?
We use stored procedures sometimes.
Yes.
White capturing, like, are they saying that since stored procedure is like an object in database, right? And you have a bunch of statements within it, so they are kind of executed as a single unit. But to me, that sounds like saying a transaction, right? That's essentially so. I mean, I understand stored procedures, but I am a little confused with what they are trying to say here. Like how they are distinguishing transactions. They're putting transactions, which are a bunch of statements by themselves within stored procedures, and they're putting a, I'm not sure about this bullet
Okay.
point, but yeah.
Yeah, so
book has a pretty, I think there are a few things that are missing over here, right? Like which the book kind of tells us why the necessity for a stored procedure. There are two conditions the book talks about, right? Like, so right now they're talking about a single threaded execution model, right? So which means you have only one thread executing, and they're talking about interactive multi-statement transactions, right? Where there is actually an interaction between the user and the
Right.
Like so on the program, right? Like so on the application. So for that, they're saying, instead of every time taking the input from the user and then executing this as multiple statements, if that entire block can actually be pushed into a stored procedure, so then it's like you issue the statement once, and then the stored procedure can actually take care of completing the transaction in one shot. So the book has a diagram that explains it a little bit more neater.
Yeah, let me pull up that diagram.
Yeah, I mean, parameterized stored procedure, all of that I have used also. So,
Okay.
Exactly this one. Yeah.
Mm-hmm. Can you explain this diagram if you have a better understanding of this?
So so we have these multiple statements. I mean, I think they're taking the same Bob and Alice example, right? Like, so you're executing the first select query, so which is actually a statement by itself, right? Like, so, and then you're looking at the results of that, and then you're issuing a next statement based on that. You're issuing a next statement to the database, which is the update query, right? So that's what the first layer kind of tells us, right? Like, so there's one round trip, and then you get the result, and then in the application. So what is happening is, so the first you issue a query to the database, right? Like, so that's the first set of arrows we see, the first select, and then the application is executing the if call. Right. Yeah, exactly. So that's the second one that we see, right? So, and then based on the if call, then the application is executing the next update to the database.
Yeah. So these are basically two HTTP requests. If you have a database on cloud.
Yes.
So you're making first HTTP request, then waiting for the results, and then doing some calculation, then making it to a second HTTP request.
Exactly, right? Like, so then they say, what, if there is a way to express what we are trying to do as a single block, as a stored procedure, so then you have the entire application just executed as a single statement, right? Like, so in this case, that select star and then that if and then the update can actually be executed in one single statement using this already using a set of statements that is here in the database, right? Like, so where you're checking simultaneously and you're only taking it off if the condition, you're only making that update if the condition is true.
And basically, just to add to what John is saying, so you're checking this if condition also. It's all a part of your, what we call PL SQL, like procedural SQL code. So you're going back to application, hitting the database again. That's where I was confused what they're talking about, but this explains that.
Yeah, right. Okay, yeah. So you're not making two network call. Whatever you have to do, you are storing that entire procedure so that you don't do these multiple calls. And then the database can take care of executing this thing in a single thread, right?
Yes, atomically.
Yeah, atomically in a single thread.
Just to notice here is, like in the first one, we pass like shift ID only. And then in the second call, we pass like Bob, which is needed for that transaction. So when we are running stored procedure, we define parameters in such a way that we pass everything that's needed for that procedure.
Yeah.
And I was, I believe stored procedure are also in general performance-wise. They are, because let's say you run the same stored procedure with some other arguments, right? Tom and shift ID 100, right? So in that case, like stored procedures are also like compiled. So you don't have to, on the database side, I think it saves the overhead, of generating a plan and all of that. So, but that's a different topic, I mean, not things up, but.
Yeah. Okay, great. So now, so let's see like what are the pros and cons of this stored procedure. So by the way, I agree with Johnny, like this summary, it misses a lot of things, and book has things explained really well. So let me know if I have missed out something. Okay, so pros and cons of stored procedure. Each database vendor has its own language for stored procedures. right? Yeah, so this makes sense that each database will have its own language, so there is no universal way of specifying it. Code running in a database is difficult to manage compared to an application server. And I don't fully understand this. Yeah, like obviously if you're running the code on application server, you have full control on the code, whereas here you have given it to the database. But I don't know like what they mean by difficult to.
I think the next point might.
Oh yeah. They say in the book that it's harder to debug and all, right? So if you have to debug or if you have to add some logs or something, right? You can add those logs in your code. But if you have submitted that code to database, it's hard for you to debug, right?
Well, I think that's a little subjective statement, right? Given how deep you are in databases, there are a lot of like if you talk to DBAs, right? They have a lot of tricks and stuff to do that. I look at it more as what they have in the next point, right? All this concurrency and all this going on. If you look at one like one database instance is shared by many application servers, right? You have one SQL server installed, and you might be handling requests from different servers, right? So I think handling all of that and while making all of that transparent to the user, right? Users, let's say in their application code, they just think that they are the ones using database and they don't employ any concurrency methods, but database has to take care of all of that, right? If it's being hit. But yeah, I mean, that's one way.
So it's an advantage or disadvantage? A
No,
database?
it's not advantage, disadvantage. I'm looking at it as a complexity, like the point number 2, right? Where they say code running in database is difficult to.
No, actually, I can give more points. So another is version control, right? So if you have your own code in the application code, you have this version control and all, where you can see if you have made changes to the stored procedures, you can see what all those things are, because everything is on your control. Now here, if you have submitted that to the database and it's a stored procedure, it's hard to maintain the version control also, right? So they're talking about this, that basically, yeah, so this is the line from book. Code running in the database is difficult to manage compared to application server. It's hard to debug, more awkward to keep in version control and deploy, trickier to test, and difficult to integrate with a metrics collection system for monitoring. Right, so yeah. Okay, a database is often more performance sensitive than an application server because a single database instance is often shared by many application servers. Right, okay, this also makes sense that basically what we are saying here is that so this stored procedure, if we have stored it in a database, we have given database more responsibility, and generally database itself has a lot of responsibilities. So because it is shared by many application servers, so now that some piece of application logic, if you have put it in the database, you have like given some more responsibility to database, which itself is being shared by multiple application server, and it already has a lot of responsibility. So that's why this is also a kind of a disadvantage of using stored procedures, that kind of you have overloaded your database with implementing that stored procedure. Modern implementation of stored procedures have abandoned PL/SQL and use existing general purpose programming language instead, like Java and all. Okay. So yeah, I have never used stored procedure, and I don't know if there are any problems with using PL and SQL, but like one thing I can think of is that using Java and such language are more universally known, so they have their advantages than using some database specific language. Okay. So now another approach of like doing these serial executions, right, is partitioning. So what you can do is you can partition your database in such a way, which we have discussed last time also, that so you have to be careful during the partitioning that whatever data values that will be part of one transaction are part of one partition. So if you have splitted your database in partitions, then you can execute multiple transactions in independent partitions, right? And also, so you don't have the problem of these concurrency, because you have splitted the database into those partitions. Those partitions are independent, so they can be independently executed in parallel. But within the same partition, you have to follow all of these above rules that you have to, like within a partition, you have to take care of serialization. So that's the another approach here. So for applications with high write throughput, a single threaded transaction can become a serious bottleneck, right? So then if you can find a way of partitioning your database so that each transaction only needs to read and write data within that single partition, then each partition can have its own transaction processing thread running independently from others. When transactions can be single partition depends very much on the structure of the database, of the data used by the application, right? Yeah. So the thing you have to be careful about here is that, so your each partition has to be executed as a single thread. So you have to be careful about partitioning your database such that you should not make any transactions which are across the partitions. Okay, so now moving on to summary. Should we move to summary, or has anyone have to add something over here? Okay. So a viable way of achieving serializable isolation with certain constraints, every transactions must be small and fast, because it takes only one slow transaction to stall all transaction processing. So the approach which we have discussed, right? Basically, this entire approach was that you are actually implementing your transaction serially. You are actually implementing your transaction one after another, right? So that's why you have to be sure that these transactions are small, because if your transaction is taking a lot of time, then all the consecutive transactions are blocked on your this transaction, right? And so the second thing is this, that this scenario best suits the requirement of a data set which can entirely fit in the memory, right? Write throughput must be low enough to be handled on a single CPU core, or transaction needs to be partitioned without requiring cross-partition coordination, right? So write throughput must be low. Why? Okay. So what is the definition of throughput? Throughput is how much write operations we can perform in a unit of time, right? Is that correct? That is called throughput, right?
Yeah.
So yeah, so now, so the definition of throughput, number of write operations we can perform in a unit of time. So if it is high, right? If your application has high write throughput, then it will be hard to be handled by a single CPU, right? Because you are executing these transactions serially. So that's why your system should have low write throughput, or your transactions should be, or your data set should be divided into partitions so that those individual partitions can be operated simultaneously and concurrently, and then you can obtain high write throughput. Cross-partition transactions are possible, but there is hard limit to the extent to which they can be used. This is, has this been explained more in book? I don't understand this. Yeah, no, I think in the book also they have exactly mentioned this one line. Yeah.
The hard limit part, but I guess they might be alluding to like if your data is partitioned, right? For example, a join query comes in and it to read data from two different partitions, right? And then give the result. Then that's possible, but what is the overhead? Like maybe the overhead becomes too high, right? If you are partitioning and you're doing all these cross partition transactions where you're pulling data from all multiple partitions. I guess that's what they mean.
Yeah.
That's
yeah.
what you like, I know all these databases like not, I think like Redshift and even actually the ones on cloud in general, not even specifically to quote anyone because I'm not 100% sure on the names. But what they try to do is when they are doing distributed, queries like which are split across different nodes or different partitions. The idea of one of the partitioning criteria is how do we keep the data which requires joins, right, on the same partition as much as possible, right? So that do all this.
Yeah, because if your partitions are on different machines,
Right.
then you will have high overhead of joining. And the other approaches, other problem is that you have to bring the data in memory to join, right? To perform the join. And so if those two data partitions are in different
Location.
on different systems, then bringing them in memory at one place, it's harder. And that's why we say, right, that like SQL and these, so if you want to distribute your data, SQL and all have problems. So the problem is only that if you have partitioned the data in such a way that you need to join across different partitions. But if you can partition your data in such a way that you don't need join across partition, then SQL and all these relational databases are very good, right? They don't have any problem. So that's why, like, I see a lot of time people saying that I have to distribute the data on multiple nodes, so I will use a NoSQL database. But there should be more explanation that it's not like universally true that if you have large set of data that needs to be stored on more than one node, then you straight away go to NoSQL. Like in some situation, even SQL database can do a good performance, right?
There is a very interesting caveat there. So to read about NoSQL, some of them don't even allow joins. And that is one of the things. So when people make a blanket statement that, hey, I'm going for NoSQL, it's very important that we understand why that's the case. It's not, I find this statement quite, interesting and debatable when we say relational databases cannot do it. If you say SQL, right, it's on Azure, SQL flavors are on Azure. Stuff like that. So, I mean, Microsoft SQL Server on Azure and even Redshift, which is a columnar database, right? It's not key value or a NoSQL per se. So it's important to really have that distinction clear that some NoSQL don't even allow joins. So if your database is such that you can have that, then sure. But that's not to say that relational cannot do it.
Yeah. Yeah, I totally agree. I mean, this has been mentioned at many places, but they don't explain in detail. So exactly, so DP, as what you're saying, that so you are saying that they are saying that don't use we can use NoSQL if you have to distribute the data, but you are using NoSQL because they don't allow joins. You can do the same thing with SQL also. If you are not using joins, then you can distribute the data with SQL also on multiple machines, and you won't have those problems.
Also, like, when your application is such or your data is such that, okay, you can get away with joins, right? You can have it organized in such a way. Then this whole discussion, right, of distributing and reading from multiple is kind of weakened, right? It doesn't really, it's a different, my point is like, it's not an apples to apples comparison, right?
Yeah, exactly. Yeah.
To add to that cross partition transaction, so even that's we do. That we don't need the join in that case. So we read that in the chapter 6 partition. So when we have to create the secondary index, so during that transaction we have to update all these cross partition to there are two techniques for the second index. One is that the document base, and the second is that called the global indexing. So in case of global indexing, we are crossing the partition.
No, I think that's true, but it again comes back to what is the point at which you're talking about crossing the partition. When you're updating the index, right, which is more like write time, right?
Right.
Operation. Either you can cross the partitions at that time, and at the reads, you don't have to cross it, right? Or you don't cross it at write time, you keep it partition, but then at the read time, you have to do. So I think cross partitioning in that case, I don't know if Praveen was speaking. So basically,
Because when you are writing, so you are cross partitioning and updating all the partition, the corresponding partition where the second index needs to be updated.
Right. So that is a cross partition transaction, right?
No,
Yes.
but that's my point, right? When you say cross partition transaction, unless you add the write or read part, right, it's always going to be a cross partition, right?
Yeah, I agree. I think both, as you explained, either at write time or at read time, you have to go across the partition. So in both the scenarios, I will say that it is a cross partition transaction. Either you do at the read time or you do at the write time.
Right.
So basically, so you have these multiple partitions, right? So here we are saying that you can do operations simultaneously in different partitions, but if another transaction comes, it has to wait serially, like this should finish and then second should finish. Now, if we have to do something across two partitions, then we can do it. So that basically then that transaction has blocked these two partitions. And now if any other request or transactions come to these partitions, it will be blocked that first this cross partition transaction should complete, and then the next transaction can come. So that's why I think they are saying that these cross partition transactions are possible, but they are limited because then you are blocking all of those partitions from any other subsequent transactions. DP, are you saying something?
No, I think this is good.
Yeah. Okay. So now we have, I think, 15 minutes, and I think this two-phase locking is a bigger topic. Have they explained two-phase locking in this, or have they not explained in this section? Because in this book, I have also read the explanation of two-phase locking, how it actually works.
There are two things. So So to be clear, that two-phase locking is different than two-phase commit.
Oh, right. Sorry. Yeah, I was talking about two-phase commit. Yeah, yeah. Yeah, that's right.
Yeah,
Okay.
let's.
So, yeah, that two-phase locking is nothing. It's just a read-write lock.
Okay.
So
So,
in normal programming, we do read-write locking, read-write lock, where read is shared and write is exclusive.
yeah, yeah.
So
So
basically, like the second point here, right? That writers are not blocking other writers, but they're also blocking readers.
Yeah, yeah.
yes.
But maybe like, how about like we just take this on next time? And I think this is a good talking point, right?
Yeah.
We covered serializability and all that stuff.
Yeah.
I just want to
Okay.
spend a few minutes. Yeah.
I have a question actually. Can I go ahead?
Yeah, yeah.
Yeah.
Yeah. So when we were discussing about the doctor example, where both the doctors decided to go on vacation at the same time, there that situation could also be like prevented by some constraint. For example, if you decide to keep that the number of doctors or number of doctors on shift does not fall below one, or if same goes for meeting rooms, right? If the number of users that book that particular meeting room does not go beyond one, those situation could be handled by
Right. Those are
constraints.
like invariants and constraints. Yeah.
Yeah, yeah,
Yeah,
yeah.
like then why, like what is a better situation, like which one we should go for, like serializability that we have been talking about right now, or like going with the constraints? Because I thought like all these three examples, even the username one can be solved with constraint. You can just have a unique username.
I didn't think of my. What, somebody saying something. So my perspective there was that it's not about saying that this is the serializability. You have to go with serializability to solve this problem. The way I was looking at this is an example to illustrate serializability. Like if you were to go with it, how will you do it? Not to say that this is the right solution for it, right?
Yeah, but what will be the cases where I can just use serializability and nothing else? Will there be a case, or like
I'm sure there is a design decision behind it, but to find a concrete, like real world example where it's used, that's something to check.
Okay, so the question is that can all these problems be solved by database constraints, or do we
Not
need
that.
these kind of?
No, I don't think that. Okay, so if that's the point, then like I haven't read it completely, but from what I know, it's not like you can solve all this problem with constraints. For example, you may solve one, but like phantom reads, right? Uh, if we go step by step, like I was doing actually a demo on this, trying to do some real world examples. So constraints can help you in certain ways, but definitely not to solve every problem. And to really, help us understand why that's not the case, we may have to just, go over a few examples to come up with a counter example, right? To show that constraint will not help here. But I mean, one thing is like if we look at there are 4 or 5 problems, right? Dirty reads, repeatable reads, phantom reads, right skew, all of these lost update. So I think if we list out all of them, constraints will not solve all the problems. I think serializable isolation is the strongest one, and yeah, serializable snapshot isolation in general. I don't know how far that answers, but because I
So
haven't.
that there are some issues with SSSI. I mean, though we will read it next week, but there are some issues with that too.
Right. Yeah.
And to you, Shreya,
Mhm.
regarding that, the solving the problem with the constant, yes, there is a trade. We can solve it, but you know that when we solve this type of problem with the constant, so you sometimes depends on the scenario. User experience may be bad, as we are allowing both the user to actually go and update the record, but only one will succeed, right?
That's a very good point. Yeah, because even if you have constraint, right? Let's say you say let's say number of doctors on on vacation cannot go below like 5. above 5. This whole thing is dealing with concurrency, right? What if two users sees the same, number and they try to update the same thing?
Mhm.
So yeah.
So no, but has anyone any experience with constraint? Because are we saying that both will be returned success, but because of database constraint, only one of the updates will be actually returned to the database? I thought that because of constraint, database will actually return failure to
Yeah,
another.
that's what I'm saying. Saying that, I mean, only one will succeed, one will fail, but the user experience for the second user, the experience will be bad. That user will say that, okay, why I spend so much time to enter all these information?
But isn't the case with materializing conflicts
But
also?
yeah,
No?
that will always happen, right? In which in all the
So
situations, if
in
two things are
materializing, we are locking upfront.
Okay.
Before moving
Uh,
forward, we acquiring the lock and then allowing to make some changes.
Right. We are not letting user do a bunch of operations and then later on saying, oh, this won't work, right?
then how concurrency is handled? Okay, you have lock and then you won't allow the other user to modify
To make
anything.
anything, any change.
but no, but isn't will it happen? Won't it happen like this? So both will have to acquire lock, right? So
So
one,
only one will acquire the lock.
yeah. So one will acquire the lock. So second will be waiting for the lock, right?
Right.
Second will not say that I was not able to acquire the lock, so I'm failing. It will wait for lock to be acquired, and when it acquires the lock, then or it will fail at the point when it is not able to acquire the lock.
No,
Right.
when
So
it will wait, and when it acquire the lock, at that time, he or she will not be able to make any changes as the condition is false now.
So then again, we are returning false to
Turning
the user,
failure,
right?
yeah.
Yeah,
He's
so that's why I'm
waiting.
saying it's a trade how we want to actually implement
and
or
that's
what,
and that's
based on our application.
Yes, and that's where the isolation level concept comes in. If you look at how different isolation levels are dealing with these locks, right? If, for example, if you go all the way to fundamental, read and commit, I just really want to wrap it up in another 1 minute because I want to discuss the scheduling part. So the thing is, we can take this question next time, but
Okay,
my
let's stop the recording first. For,
Yeah.
I
Okay.
mean, for the next session, there will be separate recording.